Welcome to today's Military and Aerospace Electronics online panel discussion, Artificial Intelligence and Machine Learning at the Edge. Developing artificial intelligence and machine learning enabling technologies are among the highest priorities of the U.S. military, particularly for applications that must operate reliably on the forward edge of the battlefield. Today's high-performance embedded computing designs that involve heterogeneous combinations of central processing units, general-purpose graphics processing units, and field-programmable gate arrays are considered some of the chief enablers for AI and machine learning at the edge. This online panel discussion with notable industry experts will explore the latest trends in microprocessors, GPGPUs, FPGAs, high-speed switch fabrics, encryption, trusted computing, and data security for the latest applications of AI and machine learning, to promising applications like real-time target identification, electronic warfare, and digital signal processing, and even advanced radar. Our panelists today are Nigel Forrester, Director of Strategy at Concurrent Technologies, Ryan Jansen, Chief Architect at New Wave DV, and Noah Donaldson, Chief Technical Officer at Annapolis Micro Systems. There will be no formal presentations during today's panel discussion, so let's dive right into our questions. The first one I have is, some advanced AI research relies on the so-called heterogeneous architectures that involve FPGAs, GPGPUs, and more conventional CPUs. And this is a question really for everybody, what are some of the advantages and disadvantages of such a heterogeneous computing architecture for developing AI at the edge? Nigel, why don't we start with you?
Okay, well, that's a great leading question because every AI inferencing application at the edge is slightly different. And like most other technologies, there is not one solution that matches every eventuality. So, for example, the CPUs, which I'm most familiar with, they're sort of swapsy optimized. So they give you a reasonable level of power within a relatively short space frame, usually a single slot, and they're also optimized really for really good decision making and exception processing. So in some AI applications, a good example might be RF capture and analysis. CPUs can perform really well. However, if you have, or you want very low latency, for example, or you want lots of flexibility for superior performance, adding an FPGA as a co-processor into that, or running an FPGA completely standalone, which some of our other speakers have got great experience of, gives you much better performance. And if you have perhaps a very parallel AI application, so a good example being image processing, then having a GPGPU can be a very valuable way of accelerating that application. So from my perspective, it's all about matching the technology to the type of application that you're doing.
Okay, why don't we move on? Ryan, do you want to take that?
Yeah, sure. I think as Nigel said, there's lots of different applications for AI and machine learning, and you really want to use the best tool for the job. So we see lots of customers that are putting CPUs, GPUs, and FPGAs all in the same box to work together, and you can use those technologies where best suited. The general purpose processor is kind of a generalist and can do lots of different things well. It's very well suited, for software abstraction as well. And there's lots of developers out there that can work in that environment. If you look at an FPGA, it's can do a lot of things in parallel at the same time, and it's more specialized. But you also have a more specialized skill set sometimes that you need to have to be able to put algorithms into the FPGA to run efficiently, but you might see gains of power per performance in the FPGA. And then, the GPU is very well suited for some of the parallel applications as well, especially video processing. And it has a really nice software ecosystem there as well, allowing you to quickly get an algorithm running in there. So by having all three available, you can really make use of the best tool that's there, optimize your power, and kind of suit the time to market for that application as well. So you can really trade off and optimize for your application.
Okay. Noah, the question is advantages and disadvantages of the heterogeneous architecture. What are some of your thoughts?
Mm-hmm. Yeah. So Nigel and Ryan brought up a lot of great aspects. Yeah, I mean, a clear advantage, like they pointed out, is the flexibility of being able to, no matter what your application may be, and if your application may change, from today till tomorrow or next year, you can have different technologies available if you have a heterogeneous architecture. Whereas, once you lock in on a particular, narrower architecture, you're limited on the applications or the capability of those applications. Potential disadvantages are, of course, if you're going to have slots or areas in your architecture for all these types of technologies, obviously, you may use some of them more than others for some applications. So, it may ultimately lead to a larger system, but a more flexible system. So there are pros and cons, of course.
All right. Well, Noah, I wanted to continue now. When we look at the different processors and isolation, what is the FPGA's role and what are its strengths and weaknesses in architecting AI and machine learning at the edge?
Mm-hmm. So the FPGA, it's a harder processor to write an application for, but it can be well suited to, as it's been brought up, a low latency or parallel processed type of application. It has it has low power relative to, for instance, a GPGPU in certain applications. And some of the FPGAs are becoming, even more suited for AI. Things like Xilinx, now AMD, introducing AI engines into their parts, which are essentially vector processors, to aid in some kind of AI functions that one might want to implement right alongside the FPGA fabric. So that's kind of how I see that fitting in.
Okay. Nigel, the question is about FPGAs. What do you see as their strengths and weaknesses in AI at the edge?
Yes, I don't have a huge amount of experience of FPGAs, but very much as Ryan was articulating, they are the most flexible, but and definitely we've done some benchmarks internally to sort of compare FPGA plus CPU and CPU plus GPU and CPU on its own, and the latency that you can achieve even with a relatively unoptimized application, we found was significantly better with an FPGA-based solution. But that was using both a CPU and an FPGA sort of closely coupled together. So you get effectively the bit of the best of both worlds there, because you're leveraging the strength of the CPU and the FPGA. That's really all I can comment on, because I don't have, as I said, a huge amount of experience of FPGAs personally.
Okay, Ryan. What about FPGAs?
Yeah, I think one of their big advantages is that they're programmable, so you can really tailor make your application and suit it to your exact needs. So if you need a certain amount of latency, you can get that with the FPGA. You can optimize the number of resources that you're using, and so you can really make that custom application that suits your needs just right. Now that does come at the expense of development time often. To do the same application in a CPU and on an FPGA or even a GPU, it might take more time and more specialized skill set, but you're going to end up with something that's going to be the lowest latency, highest throughput and oftentimes the least amount of power for the performance that you're getting in the FPGA.
Okay.
And I was just going to say, FPGAs today as well have a lot of building blocks that are there for you too, as far as crypto, memory interfaces. There's lots of different pieces that are there that are making them easier to use as well.
Okay. Well, Ryan, why don't we turn our attention to GPGPUs? What are their strengths and weaknesses, and where do they really shine in AI at the edge?
So I think GPGPUs, they really shine where you have lots of vector math operations to do in parallel at the same time. So rather than doing something sequentially, you can do a whole bunch of repetitive processes all simultaneously in a row. I think the other huge advantage that they have going for them right now is just the software, the tool chain that's all set up and built around them. NVIDIA is one of the leaders in FPGAs, and they invest an incredible amount of money into their tool chain and tool set. So if you have, if you want to get something that's high performance and you want to get it up and running relatively quickly, a GPU is a great option for that.
Okay. Noah, what do you think about GPGPUs for AI at the edge?
Yeah, I'd kind of echo what Ryan says. Quick to develop an application, because NVIDIA has, a lot of example applications which can be, modified and adapted for, defense aerospace type of use. And so that's, I think one of their main advantages. Their architecture of the parts, of course, themselves are, well suited for certain aspects of AI as well.
Okay. Nigel, what do you think about GPGPUs for AI at the edge?
Yeah, so that's where I have got a bit more experience. So from both the aspect of using NVIDIA secondary GPGPU with one of our Intel processors. At the recent MOSA summit in the US a week ago, we were demonstrating an AI visual recognition application running on a SOSA-aligned CPU and GPGPU as a partner pair. Very, very easy to get up and running, highly performant, a very good software ecosystem. But I've also got quite a lot of experience of using the integrated GPGPUs that come with the Intel processors. And they are not as performant as a separate NVIDIA GPGPU board. However, you can do in a single slot a really very well optimized AI inferencing application, particularly on a video or visual, either still images or video images, by using that integrated GPGPU. And again, it's really the aspects of the GPGPU where we've got lots of parallel processing that sort of excel at that type of AI application, where it's effectively splitting the problem down into thousands of little tiny problems, and each GPGPU core or execution engine or shader or whatever it is actually solves that little bit of the problem for you in a very efficient way. So yeah, there's definitely a play, and I would say from our experience that the NVIDIA ecosystem, where we've got a key partner that we typically work with to provide that type of capability, it works really well. I've seen quite a few customer applications for that type of combination, and we've seen a few for the sort of straight Intel CPU and GPGPU.
Okay. Well, Nigel, let's stay with you. So, we've talked about FPGAs and GPGPUs. What about the traditional CPU, the Intel type or Intel type class of CPUs? What are their roles in AI at the edge, and where are their strengths and weaknesses?
Yeah, as I mentioned right at the start of the webinar, we've seen a couple of AI applications that are for RF sensitive applications, where you're trying to determine who's broadcasting at what frequencies and where they are and what bands they're on, and or power they're broadcasting at and things like that. So actually a CPU is quite performant enough for those type of relatively straightforward AI applications that often require quite a bit of exception processing or decision type making. You know, if you detect something, then you need to go off and do something about it. So CPU actually works really well there. So again, there's a good software ecosystem. In our case, we're using Intel CPUs. Intel has a not as well known as a tool as NVIDIA, but their offering in this space is OpenVINO, which spans, again, it's a heterogeneous compute tool that spans across the Intel CPUs, GPGPUs, and Intel FPGAs. So basically, you throw a bunch of resources at it, and if you've only got a CPU, it works on a CPU. If you've got a CPU and GPGPU, it works faster and more efficiently. But it gives you a very easy way to evaluate how, you know, what you can do with AI. So if you're actually trying to start out on an AI application and you just want to try some things out, and say that's a very cost-effective and easy way of doing it, even if you decide that you want a more performance solution at the end of the day, that you can then work on, you know, as a real project.
Okay, Ryan, what do you think about the role of CPUs and AI at the edge?
All right, I mean, CPUs today are very capable, and you know, I think things that can be done in them, it's oftentimes a good place to you know, run your applications. I think especially in this heterogeneous environment that we're talking about, they serve a really nice role in kind of orchestrating and commanding and controlling everything. There's very good, you know, interfaces for sharing, you know, memory between the various elements there, and the CPU often can manage and kick those things off as well. So.
Okay, Noah, what are your thoughts about CPUs and AI at the edge?
Yeah, we're seeing our customers use them most, like Ryan said, for sort of command and control of a system, and so now it partly comes from you know, the types of customers we interact with, but we see, you know, the FPGAs kind of being on the front end of at least the electromagnetic and sometimes video systems, and then you know, feeding that back, you know, often to a CPU, maybe to a GPU as well. But there's most always you know, an Intel CPU involved at some level.
Okay.
And John, can I just add
Yes,
one more
please.
comment there? So
Please.
I forgot to mention that, like all of these solutions, they are developing much more rounded capability. So in future generation Intel processor products, we'll be able to introduce neural processing units into that hardware, you know, offering, which again, the software, algorithms will take advantage of, sort of invisibly to you as a user. Ryan and Noah are mentioning other, you know, accelerator and crypto engines that you get in all of the different types of solutions. So we shouldn't forget that this is very much, you know, the AI is still very much developing environment. There's a lot more capability to come. The manufacturers of the technology have recognized that, and they're building additional capability all the time to make AI inferencing work better.
Yeah, I mean, that's a good point, Nigel. Even, you know, I think Noah mentioned the AI engines that are part of the Xilinx FPGA family, and now that AMD has bought them, they're looking at, you know, providing those AI engines in AMD x86 processor chips moving forward as well, so you can make use of them there. So this ecosystem is growing, and we're talking about heterogeneous computing, you know, in a slot by slot basis right now, but it's moving to the board level and to the package level and to the chip level very quickly.
Okay, we've got a question from our audience, and that is, does anybody have any real experience using the Xilinx Versal AI Core? And if yes, how does it compare with others, you know, other CPUs, GPGPUs, and FPGAs? Who'd like to take that one? Maybe Noah?
So our applications team is just starting to work on that. So I don't have, benchmark comparisons that I could speak to just yet. I think in another month or so we will have some, but we're starting to do some of that analysis now. I can say that.
Okay.
Yeah,
Nigel, what do you think? Oh, go ahead, Ryan.
I was going to say, we do Xilinx FPGAs at New Wave as well. So we have experience with the Versal family as well. And we're doing work with the AI engines. And, we kind of see two different ways that they're being used. One is to, in more of the traditional digital signal processing sense. And that, they're set up to do, FFTs and filtering and beamforming and radar. And there's advantages to them there, but also on the AI machine learning side, particularly on the inferencing side, we're seeing advantages there anywhere where there's vector math operations done. And Xilinx has shown in some of their papers that they are achieving better performance per watt, that running a similar algorithm in the AI cores than they are on some of the GPUs, but it is very dependent on the application that you're running. So.
Okay, Nigel, what are your thoughts?
Nothing ground shattering to add. Obviously, we work with a number of partners like those on the call today who've got much more experience with the different types of FPGA. So we've been working with companies who have Versal capability. But my bad, I've not actually asked specifically if there's any benchmarks that they could share for us on AI at this stage. But it's a great question.
Okay. All right, we've got a question from our friends at the Air Force Research Lab, and that is data leakage attack by an adversary especially critical in AI and machine learning architectures? And that is the data more valuable in those architectures than conventional computing architectures, so it needs to be safeguarded all the more? Who'd like to take that one? Ryan, maybe?
So I guess I would say that the data, data protection is important in both cases. I think there's, an aspect of, now that you've done some sort of AI algorithm and work to condense that data down, it might be even more important. I would say we're seeing that it's extremely important to protect that data in both cases, and we're seeing a significant interest, and more even requirements from our customers that data needs to be protected both as it's moving through the system and at rest. So.
Okay. Noah, what do you think?
Yeah, I agree with Ryan's statement that it's hard to say. I suppose it's a judgment call and depends on the application whether it's more or less critical, compared to non-AI ML architectures. But certainly it's critical, like it has always been before. And as these systems become more interconnected with other systems, remotely, it becomes even more critical to protect the data because it can be accessed remotely. So, we build in a lot of security features into our products and the architectures that we develop, make use of a lot of those security features that are being provided by our suppliers, those that we've spoken about, Xilinx and Intel, et cetera. So, to ensure, that there isn't a data leakage type of incident.
Okay. Nigel, anything to add?
Yeah, so I think fundamentally, we talk about AI inferencing at the edge. So what that's really doing is it's giving you some actionable intelligence based on a trained model. And so, yes, absolutely, you want to make sure that the actionable intelligence that it's providing to you is correct, and that nobody can tamper with that that capability. Is that as important or as challenging as traditional AI, as non-AI methods? I think it's probably quite similar, because other speakers talked about some of the fundamental things that we have to do to harden our products to make sure that the attack surfaces are as limited as possible, and we go through a lot of rigor in terms of testing those out. So it is very much it's an industry-wide initiative, I think, to make sure that our products are fit for purpose. And that, again, that is a continual journey. So you can't ever claim that you've got the magic solution, because there will always be something that you need to work on. So keeping things as up to date as you can, and adding as many features as you can in terms of encryption and secure capabilities is just as necessary, in my opinion, in an AI-enabled application as any other application.
Okay. I've got a software question from the audience, and that is, what would be a computer language able to handle CPU, GPU, and FPGA simultaneously? Ryan, what do you think?
So there's a number of languages out there that can do this. I know Intel specifically has been doing a lot of work, and I think Nigel mentioned it before, where you can write software and it just basically takes the resources that are available and chooses the best resource for that particular application. Us specifically looking in FPGAs, the big thing is high level synthesis. So being able to take code that's written in C or C++ and compile that into RTL that can actually be instantiated on an FPGA. That's a big enabler to all of these technologies. And if you look at what Xilinx has been trying to do, they're big proponents of HLS, but also they're doing some stuff with what they call Vitis and Vitis AI, and that's allowing you to take some of the open source AI frameworks out there like PyTorch or TensorFlow that get used a lot, and actually use those languages and then implement your inference on the FPGAs using that thing. So I think there's a number of them out there, but a big piece of that is that high level synthesis, so that you can have a common language that you're writing code in, and it can understand what to do with that and the different processing elements.
Okay. Nigel, what do you think?
Yeah, I'll give you a couple of other examples or references that you might want to go and look at. So not specific to AI applications, but OpenCL has been around a very long time. That was devised as an open standard for parallel programming of heterogeneous systems. There's OpenCPI, which is an open source framework for doing the same sort of thing on heterogeneous embedded systems. I mentioned OpenVINO. There's both a completely open version of OpenVINO, and there's also an Intel-specific version, which is wholly designed for running AI inferencing at the edge. So basically, it takes the output of a trained model, it turns it into an intermediate reference type situation using the tool, and there's all sorts of optimization things you can do around that OpenVINO. So very easy to use for AI applications. And then more generally, Intel's got another tool now that they call OneAPI. And OneAPI, sort of loosely based on the idea of OpenVINO, it's a unified model based on data parallel C++ for data-centric workloads on CPUs, GPUs, and FPGAs. Although OneAPI is, it is restricted to Intel workloads right now. So if you want to use that on a NVIDIA GPU or a Xilinx FPGA, that's not going to be working. You're better off looking at some of the other tools that Ryan mentioned.
Okay, Noah, questions about software languages for these heterogeneous architectures?
Yeah, I was going to mention, like Nigel said, both the OpenCL and OpenCPI being the non-vendor specific languages or tools that I've seen our customers are most interested in. I guess I'd say I see a lot of interest in these. I haven't yet seen so many customers successfully implementing them or necessarily trying to implement them. So it's unclear to me, just how much uptake there is on those. it certainly would be very useful if they can be successful in developing an efficient application that can be more quickly and easily developed and ported between different architectures.
Okay, got a fairly long question here, and that is, are you developing AI architectures for the edge and enterprise comms challenge? If an edge client asks a question, AI will search for an edge compute device. And if answers are not found, will then reach up into an enterprise cloud. In this enterprise cloud, you may need to kick off searches for the data in multiple repositories, synthesize answers, and then send them back down, summarized answers, to the edge-based client. Nigel, are you able to follow that question, and what are your thoughts?
Yeah, I mean, that's quite an interesting question. It's not, and I have to say, no, I've not come across an application in my sphere that uses sort of the ability to try and find the answer locally, and if it doesn't, then go back out to either a local network or the enterprise network to search more resources. That's absolutely possible. I mean, everything that we do that is aligned to the SOSA technology or SOSA standard is based around 100 gig Ethernet network backbone for high-speed data connectivity between resources. So it's absolutely possible to architect that type of system. I just haven't seen that done, or at least from an AI perspective, I haven't seen that done in practice yet.
Okay. Noah, what do you think?
Yeah, I haven't, specifically seen a program or platform that definitely does exactly what's being said there, but agreed that could certainly be a useful thing as long as you set up communications links that have security necessary, etc. Yeah, could be a good way to architect things.
Okay. Ryan, what do you think?
Yeah, I would say most of our customers are focused, on the what they're calling the tactical edge on the platform itself and doing the AI there. But I think you hear a lot about the connected battlefield and bringing all these pieces together. And a big piece of that is taking this enormous amount of data and pulling out the pieces of interest and making that available to all the other platforms that are part of this, with an enterprise, cloud, being part of that as well. So I think the pieces are there, and I think there's a vision there, but we're much more focused on the tactical edge and what's happening on the platform right now. So.
Okay. Another question. Are you aware regarding AI accelerator coprocessors? Do you know, have you had experience there? And if the answer is yes, can you share something about this, about this topic? What do you think, Ryan?
So I don't know if I know exactly which, particular coprocessor they're talking about, but the AI engines that we've been discussing, I would consider those an AI coprocessor. They're special processors that are suited very well for vector math operations, of which in AI inferencing, there's a lot of those. And like I said, those are on the Versal FPGAs right now. AMD is looking at putting those in their processors. And there's a number of other companies out there building processors that are suited specifically for AI applications that could be used very nicely alongside of a traditional processor as well. So I think they're here right now, and more are coming. So.
Okay, Nigel, the question is about AI accelerator coprocessors. What do you think?
Yes, I think that's exactly where we sort of have focused the majority of the discussion so far, as Ryan has articulated FPGAs and GPGPUs, that's exactly what they're often doing with a CPU host to do the command and control. The way the systems are architected is we have direct high-speed PCIe links for adjacent slots. So you've got a very high bandwidth connection between the CPU and the GPGPU, or CPU and FPGA, exactly as you would in a rack mount server. Same sort of bandwidth, same sort of rates that you're achieving. And then there are these more specialized AI engines, like neural processing engines and things like that, that are also coming into play here. So yeah, absolutely, that using accelerator engines is exactly what we're talking about.
Okay, Noah, questions about AI accelerator coprocessors. What are your thoughts?
Yeah, the same ones sort of occurred to me. The AI engines that are embedded in some of the new Xilinx AMD Versal processors are, a good example of an AI optimized coprocessor within, a fabric of other processing types.
Okay, we've got a question from our friends at Army Devcom, and that is, what about power? I've evaluated a few FPGAs, and some of them are power hungry. How do each of the processors compare in terms of power and cooling? Why don't we start with you, Noah?
Yes, so certainly some FPGAs can be power hungry. If you compare, of course, there are different sizes and processing capabilities of all the different architectures, CPU, FPGA, and GPU. I'd say kind of generally, the FPGAs and the GPUs can be the most power hungry, but I think what's really important is to look at the amount of processing you're getting on a particular application per watt, rather than just, here's one chip, how much power does it take? Broadly, it depends on the application, but broadly, many people will say that a GPU is easier to program, but very capable for AI applications. FPGAs are a little harder to program, and they may be similar amount of power to a GPU, a little bit less. You're often able to do more in fewer watts on an FPGA than a GPU. And I'm not sure, maybe Nigel would need to comment on CPUs. I'm not sure, exactly how those would fit in.
Okay. Well, Nigel, the question is about managing the power demands of FPGAs, GPGPUs, and CPUs. What are your thoughts?
Yeah, so it's a really, again, good, astute question. And I'd sort of phrase it slightly differently, is that we are in the process of developing rugged tactical edge solutions. So the sort of building blocks that we're producing are very consistent. We're often talking about, a very common form factor is 3U VPX form factor, where traditionally we've specialized in doing rugged conduction cooled products. So there you're trying to provide a product that gives you maximum and deterministic performance at an operating temperature range that typically ranges from -40 to +85 degrees C, sometimes perhaps a little bit lower, but you want the product to operate deterministically across that temperature range. Now, because of the physical restrictions, laws of physics, where you're trying to conduct heat away from some very hot components, and as we get successive generations of process, no matter who they come from, the power density of those components goes up, even if the overall power consumption remains the same. So it becomes successively more difficult to cool. We are also introducing some slightly more exotic cooling technology. So in the last 12 months, we've developed a number of airflow through boards, which we're able to raise the performance level per product, if you like, or per slot, because we're using an air-cooled product rather than just a conduction-cooled product. And I think that spans across the different technologies. It's not just the performance that you can get on a device. You have to look at it from a system or a card level, is what you can actually, cool or keep within your operating temperature limits. So it's quite a complicated answer here. I probably didn't answer the question terribly well, but there's a lot more to it than just raw performance you can extract from a device in a lab type situation.
Okay. Ryan, the question is about managing power demands in these heterogeneous AI architectures. What are your thoughts?
Yeah, I mean, if you just look at the devices themselves, if you're using the highest end device in any of these classes, they can eat up hundreds of watts of power, but you're getting an incredible amount of processing for that amount of power. So I think, as you're trying to do stuff at the edge, you really have to be, smart about what devices you're choosing and what you're trying to accomplish with those devices. Cooling and trying to get that heat out is very important. And with FPGA specifically, one thing to remember is you don't take up that full amount of power if you're not using the whole part too. So the amount of power that an FPGA is using is very dependent on the application or the FPGA load that you have running in there. And, you have to pick the right device for the job as well. We see with the latest, FPGAs, especially with the 7 nanometer technology, that static power is high. So you kind of have a high barrier of entry to start out with, but then after that, you can do a lot of processing, with that remaining power. So if you have an application that needs it, its performance per watt is probably better. But if you already have a low power application, you want to pick a device that's more suitable for that application. So.
Okay. Noah, we've got a question about balancing performance versus cost in architecting these heterogeneous architectures for AI at the edge. What are some of your thoughts about how do we balance cost and performance and, add in, some of the ruggedization and swap issues for AI at the edge?
Mm-hmm. Yeah, so there are, so of course there are different, price points from all of these different architectures as well. FPGAs do tend to be at the higher end of that scale. They partly they fit there because they're, providing sort of a density of processing and flexible capability, that the other architectures aren't able to achieve. So, there are some things that you can't do with those other architectures, like we've gone over before, in terms of lower latency, and lower power per watt. Whereas the CPUs and GPUs are generally able to come in at a lower price point comparatively.
Okay. Ryan, the question is about balancing cost and performance for AI at the edge. What are some of the considerations?
Yeah, I think one area that helps us is, the MOSA objectives and the open architectures, because we're trying to create an ecosystem where you can hopefully plug and play, with these different types of processors into one box, and then you can suit it for the application that you're up against. If you have a really high-end application that requires, a bunch of FPGAs working on a problem, you can put that in the chassis, but you can also turn around, and build one that might be more CPU or GPU intensive as well. And as these algorithms progress and over time, maybe there's new techniques and new algorithms that can do the same thing with less processing power. You have the ability in future updates to change things around as well. So I think, SOSA and MOSA are enabling people to make these trade-offs and change those more quickly over time as well.
Okay, Nigel, what do you think about balancing cost and performance?
Yeah, I agree with both speakers. I thought Ryan's point about the MOSA, the fundamental objective of MOSA and SOSA is that you can select the best in class product. So all of us are determined to get a cost-effective, the most cost-effective solution. Of course, we're going to, make sure that we sort of architect a solution to sort of fit the needs, but at the same time be as cost-effective as we possibly can. And with that MOSA structure, it enables technology transitions in future years in a much easier way than we have historically. So I think looking at the whole life cost of your system, as well as just the initial purchase cost, is a really important factor, because fundamentally the sort of products that we're doing, whether it's CPU, FPGA, or GPGPU for AI inferencing at the edge, I'd say they're cost effective, but they're not low cost.
Okay. Ryan, I've got a question for you. How do you develop products and define architectures when future algorithms and techniques to process sensor data may not yet be known?
So I think the last question really leads into this one. It's, you need an open systems architecture so that you can quickly and easily adapt the latest and greatest in class. It also allows this heterogeneous architecture where you have a number of different processors that best suit an algorithm is another key to that. And then I would say enabling lots of sensor data to come into a system, and we're doing that with 100 gig Ethernet and PCI Express across the backplane. We're enabling an environment where we can get lots of data into a system and then make that data available to a number of different types of processors across the system, and then over time allow you to upgrade to the latest and greatest thing. In the future, there's a lot of talk about neuromorphic processors, that are more modeled after the human brain versus von Neumann architecture. So if we get to a point where there's one that's ready to go and it's perfect for an algorithm you have now, you can plug that into this open system and make use of that as soon as possible instead of waiting for the next major technology upgrade. So.
Okay, Noah, what do you think?
Well, so yeah, I think having a flexible system is ideal. If you can, so many of the systems we're looking at that'll have, if we're talking about like a VPX chassis and you have multiple slots, 6 or more slots, then having a system with enough switching capability between the slots and flexible switches so that you could do Ethernet or PCIe or maybe LVDS, switching between all of those slots can be an ideal way to deal with that, because customers can pick and choose the appropriate processing for the appropriate slot in those situations. And that's something that sort of has been noticed by some end users, that more connectivity and more flexible connectivity between slots was really necessary, and so therefore a higher density switch profile was necessary. And so that's something that we've developed, with SOSA, to come up with a higher density switch profile that can be used in these chassis, so that we can achieve that flexibility of connectivity rather than having a backplane where we've assigned, certain slot to slot connections or something like that.
Okay, Nigel, what do you think?
Yeah, I was just going to say, the three vendors that are on this webinar are a great example of how we can work together as an ecosystem to deliver exactly the sort of thing that the question's alluding to. We're all working together under a common sort of architecture to offer as many solutions as we possibly can that are can flexibly be interchanged to deliver on that sort of promise of reconfigurable systems to meet your application. So yeah, I think we're sort of proving that is becoming a reality.
Okay. Noah, a question for you. How will the newest generations of FPGAs aid in high performance applications like artificial intelligence and machine learning?
Hmm. So one way they're doing that is by having these AI engines, for instance, in the Xilinx AMD newest generation. Other things they're doing are more sort of in terms of optimizing for swaps. So adding in ADCs and DACs, in some cases, very high speed ADCs and DACs. So you get a direct RF. You no longer need tuners in front of these systems. You have ADCs and DACs together with FPGA processing together in a very small package, so that you can fit that, into an edge type of system. So on a very small platform or in a very small space, at the tip of a platform.
Okay. Ryan, what do you think?
Yeah, I think they keep putting more and more capability into a smaller form factor. We've touched on the AI engines, RF as well, but they're adding lots of different building blocks into those FPGAs, including Ethernet, MAX, PCIe, not just the hardcore endpoint, but the DMA is getting put into hard silicon. You look at the RF work that Noah talked about. I think in the future we're going to see integrated optics in the package at some point as well. So they keep putting more and more things in a small space that's going to allow you to do more and more in these small form factors at the edge. So.
Okay, Nigel, anything to add?
Yes, I can't really comment so much on the hardware side, but one thing I have observed is that there's been significant advances in the software capabilities for heterogeneous compute resources. So lots of different industry standard frameworks are supported, lots of different models depending on what you're trying to do with your AI system, from speech recognition to video recognition to other types of AI algorithms that you're trying to run. So I think that we tend to concentrate perhaps a lot on the hardware side. There's an awful lot behind the scenes in the software capabilities that make those products easier to use across a much wider range of AI applications, and that spans all the different types of technologies.
Okay. Ryan, question for you, and that is, what do people mean when we start to talk about the edge, and how does the definition of, today's definition of the edge, how does it influence sensor processing architectures?
So I think at its most basic case, a lot of people look at the edge and think anything outside of the cloud or the data center is really the edge. And I think, that's a good definition, but a lot of what we've been talking about today, I've heard called maybe the tactical edge, but, on a specific platform itself, what kind of AI infrastructure can you enable at the edge? And as we continue to move forward and try to, allow sensor fusion across many different platforms, you kind of have this ecosystem where you have edge processing within a platform itself, and you want to make some of that data available to do processing in other platforms and be able to utilize that information. So I think the architectures, not only need to be able to do a considerable amount of processing on a platform, but also need to be able to put that data into nice packages that can easily be used by other devices and other platforms within the ecosystem as well.
Okay, Nigel, what do you think? What do people mean when they're talking about the edge, and how does that influence sensor processing architectures?
Yeah, so very, very similar answer in that our expectation of what we mean by the edge is typically something that is collecting data near the sensors and doing that processing locally. And that might be on an aircraft pod, it might be on a ground vehicle, it might be in some naval type platform, but it's basically doing everything that you would perhaps traditionally have captured the data and then taken it back and processed it offline. But you're now able to do that wholly actually at the at the sensor or at the edge, basically, and actually make some real life and real-time decisions based on that data, should you so want to do, or you could still store it locally and do some post-analysis, or you maybe do both.
Okay. Noah, what do you think? What is the edge and how does that influence the architecture?
Yeah, I guess I just add I think an edge term is of course very subjective, depends on your perspective, right? So, someone at a data center in a big warehouse, thinks everything outside that data center is the edge, whereas they may be communicating with a vehicle that has its own data center, which has edge devices, further out, maybe, in a sensor, in a pod, etc. Yeah, that's kind of what I would add.
Okay. I think we probably got time for one more question, and that is, when would you expect to see some of the first deployments of AI at the edge? And, looking farther out, when would you think that AI would be a routine part of sensor processing at the edge? Nigel, what do you think?
Yeah, so we believe that we've actually seen a small number of AI applications at the edge. We're not entirely able to understand exactly what's being done on those applications, because quite often our customers are a little bit reticent in sharing some of that information for obvious reasons. But fundamentally, those customers have got into their mindset is that the things that they're doing with AI at the edge are very much in terms of producing actionable intelligence. And then there's usually some other, an analyst or person in that sort of processing line that makes a decision based on that information that the sensor or the AI inferencing box is providing. So I think it's definitely out. There are applications out there. Are there lots of them? No, they're not. I think a lot of people are still using very traditional techniques right now, but those barriers are breaking down. And I think as we introduce more of these MOSA platforms that are enabled to, such that it's very easy to create the type of processing capability that you might need for more AI-based solutions, that will accelerate dramatically.
Okay. Noah, first deployments of AI at the edge, when do you think that's going to happen?
Yeah, I agree with Nigel. There are already, some few deployments going on. I do think over the next 2 to 5 years, it'll increase a lot, though, compared to what there is so far.
Okay. Ryan, your thoughts?
Yeah, I would agree with the others. I think, especially if you're looking at machine learning, I think that there's already machine learning applications at the edge that are being used today. But I expect it to grow. I mean, if you look at trying to get down, take in data and make an actionable decision based on that, and the goal to drive down that time to make that decision as small as possible is going to necessitate the need for more and more. So I expect it to grow over the next 2 to 5 years as well.
Okay. Well, unfortunately, we've run out of time. We're up at the top of the hour. So, on behalf of Military and Aerospace Electronics and Endeavor Business Media, thanks for coming. I'm John Keller, Chief Editor of Military and Aerospace Electronics.